In this video, we're going to look at creating basic differential equation models. We're not going to be solving the differential equations, but we're just going to look at how to create very basic differential equation models for applications. In this video, we're going to talk about modeling with ordinary differential equations. Now, some of the basic models to make differential equations are actually pretty easy. One thing nice about differential equations, when you're setting them up, you just have to set up the change in the value. So for example, let me start with a pretty simple example. Let's suppose X is the amount of money in the bank. And T is time. And let's say it's in years. And let's say the money in the bank, of course, would be in dollars. And let's say R is the interest as a percent. Change at, instead of percent, let's make that a decimal. And so let's have this example. So let R be the interest rate. Let's say it's going to be 5% per year. And of course, if the decimal is 0.05. And suppose you have $1,000 in the bank today. And again, let's say, again, we're going to go with T in years. Find an equation for the amount of money in the bank at any time T. Once again, we're going to say T is going to be in years. So again, when you're setting up the differential equation, all you have to start with is the change in money in the bank. So like, for example, so remember, let's say if X is the amount of money in the bank and T is time, then we want to start by finding out what's the change in X, the change amount of money over time. And now we can make a real simple relation. Let's say if you have X amount of money in the bank at any given time, then the amount it's going to change per year will be whatever's in there times the interest rate. So like R, like this. So once again, remember, we're doing right here, this is going to be the change. And let me put this down to emphasize this. That's going to be the change So it'll be the change. This represents a change in the amount of money per year. So it's going to be whatever is in there at a particular time times the interest rate. That's how much it's going to change. Not the amount that's going to be in there at any particular time, but it's going to be the amount of change. Now, our particular case, we're going to have like 5% interest. So we're going to say put a 0.05x here. So again, this is saying the amount in the bank is going to change with respect to time, dx dt, by 5% times whatever's in there. So if you have $1,000 in there, the change every year will be 0.05 times 1,000. Again, that's not the total amount in there, but it's the amount per year that it's going to change because we're doing time in years. So now we're going to try to solve this to actually get to an equation. So let's solve this differential equation. Here we can just separate the variables. And excuse me. Do you remember when you do these basic differential equations, we have to get all the variables on one side, let's say for x, and all the t's on the other side. For something like this, I just sort of cross multiply it. Then we want to integrate this. Let me put all the steps in. And I'll integrate. Now, since this is a constant, I can bring it out front. This is going to be log of x t plus c. And now again, remember, we want to solve this for x. We're looking for an equation for the amount of money in the bank at any time t. And of course, whenever you have log, we can get to the x by raising e to that power on both sides. Like this. And let me continue over here. This is going to be x. And the right-hand side. Now, notice that on the right-hand side, we can rewrite that a little bit. That can be rewritten as 0.05 e to the 0.05t times e to the c. And remember, this is a constant, right? Because e is a constant and c is a constant. So we could just call this k. Let's call this k. I'm going to put it out in front. Like this. And now we'd like to find that k. And we can find the k by using our initial condition. So our initial condition is that when we started, there was $1,000 in the bank, and that will be at time 0. So let me note that when t equals 0, the amount of money in the bank, which is x, was $1,000. And let's put that in here. And so we'll have $1,000 k e to the 0. This, of course, e to the 0 is 1. So that means k is going to be equal to $1,000. Now back to our equation up here. X 1,000 ET. So this is the equation for the amount of money that's in the bank at any time t. And you can put whatever value. You can put like 1 year here, or 1.5 years, or 2 years, and find out how much you have. And then it's important to notice the money is compounded. So, you'd think after 1 year you'd have 1,050. You actually have a little bit more if you put the number in this equation. But the most important thing I want to point out was not so much that we solved this equation, but what we started with. We wanted to set up our differential equation. And when we wanted to find a change in x with respect to t, we want to know how much x, the amount of money in the bank, changed over time. And that was equal to whatever amount you had in the bank at any particular time times the rate of change. And that would be our interest rate. So that's how we kind of started out with our equation. That's the key when we're doing these differential equations. We don't have to have the solution right away. We don't start over here. We start over here working with the change in the variable. So now we're going to set up some basic differential equations for maybe animals. So let's say X is the number of animals. Let me just say maybe fish would be a good one. Number of fish. At any time t. And again, t is the number of years. And so we want to find an equation for the number of fish in a pond. And let's say, suppose the birth rate is 1.3 per year. That would mean maybe for every fish, there 1.3 are born every year. And let's say the death rate let's go 0.9 per year. That means for like all the fish that are in the pond today, 90% of them are going to die this year, within like a year. And of course, that means some of them would carry on. That means probably their lifespan is probably a little bit more than a year. If this number was 1, that means their lifespan would be 1 year. But this is a little bit less than 1, so not all of them will die maybe at the end of the year. So the lifespan may be a little bit more than a year. So, and then once again, suppose 8,000 fish are in the pond at the beginning. So let's take a look at this. So once again, let's say, again, X is the number of fish. And so we want to know the change in the number of fish in the pond. So once again, the 1.3 birth rate per year. So that means however many fish are in the pond today, there are going to be 1.3 born every year. On the other hand, the death rate is 0.9. So whatever number of fish there are in the pond, it's going to be reduced by 0.9 times that. So we could, and now notice you can usually just combine these. And so this would be, say, dx dt, and we subtract those, be 0.4x. Now you could solve this equation just like we did for this equation a minute ago for the money in the bank. You could solve it in much the same way. Though right now we're mostly interested in setting up these equations. So now you can see what we have here. We had just say, okay, whatever number of fish are in there in the pond, multiply that by the birth rate, then subtract number in the pond times the death rate and get this. So now the general equation you could have would be maybe something like this. You have maybe, say, dx dt. You know, you could say maybe some birth rate here, death rate here. Now, sometimes these are just combined together. So usually, like, instead of giving this and this, we'll just always start out with putting them down as a net birth rate. So if the birth rate is 1.3, death rate 0.9, we'll just start with 0.4. So the equation is very similar to what we had for money in the bank. So it would be something like that. So this would be a pretty basic equation, where a lot of times this is referred, to the rate of change, or sometimes they'll call it the maybe the birth rate, even though it's really the net between the birth and death. But the main idea is the amount of net increase of fish in the pond. Now, there's something very interesting we're going to look at here, is that, let's say all these fish are in the pond. And again, you can see, as long as this is positive, when you're dealing with the dx dt, as long as this is positive number here, that means there's going to be an increase. If this net had been negative, it's going to be a decrease. So this could continue to grow, and theoretically, this is just going to keep growing and growing and growing, because it's always going to grow at this value here, whatever R is. But suppose, again, let's say the pond is pretty small, and, as the fish are getting more and more, they're filling up the pond, they're starting to run into each other, and they're competing for food. It doesn't seem to make sense that the fish would just get big, grow more and more and more. There will be more and more population of fish, because it's just going to be too much for the pond. To model the fact that a pond or a forest or any place like that has a limit to the number of animals that can survive there, we have what's called a carrying capacity. The carrying capacity is the maximum number of animals, in this case, the maximum number of fish that could survive in a pond, due to the fact that the resources are limited. Like, for example, the space is limited, the food is limited. So the pond can't sustain any more animals, any more fish than a given amount defined by this carrying capacity. Like, say, for example, maybe this pond can only hold 25,000 fish, that at least that can sustain that many. So that means once you get up to that point, fish will start dying because there's not enough food for all the fish, or, just because they're close together, they could be running into each other and, hurting each other. So in many situations, we might have something like this called the carrying capacity, which limits the number of animals you have in a certain context. And again, the context could be the forest, or it could be, any place where maybe resources are limited. You might have this carrying capacity. So for differential equations like this, we often will have a what they call a logistic growth equation. And so once again, let's say X is the number of fish in the pond at any given time. Then the change in X will be, say, that R times X here. But the only thing is, there's going to be like a limitation. So so R times X, but in between there, we're going to put a term like this. So instead of Rx, we have this logistic term. And notice what happens with this term here. Notice as X gets closer and closer to K, so let's say in this case, maybe K is 25,000, and let's say that gets closer. Let's say the total number of fish in the pond gets to, say, 24,000. Notice this will be very close to 1, maybe a little bit less than 1, and then 1 minus that number is going to be a very small number. And that's going to mean the rate of change at that point is going to be less as X gets bigger. And that makes sense. The more fish in the pond, the slower it's going to grow. because of the limited resources. So like I said, if we're up to, let's say, 24,000, for example, let me put that in my calculator. If if at any time the population of fish gets up to 24,000 and the limit's 25,000, then 24,000 divided by 25,000 is going to be, I got 0.96 on my calculator. And then this difference, that'll be 1 minus 0.96 is 0.04. So that means that at that point, this rate of change is going to be all multiplied by 0.04, which is going to reduce that rate of change significantly. And then, of course, once x gets to 25,000, this is going to be 1 over 1, and then it'll be 1 minus 1, and this will go to 0, and there'll be no rate of change at all. It won't grow at all once it gets to that point. So this is something common when you're modeling the amount of animals, say fish in a pond or bears in the forest. We will have this logistic term included. So this might be our differential equation for a case like that. So again, if we apply this to our last example, where we had, say, a net growth rate of 0.4, then in that case, this equation will be 0.4 times 1 minus x divided by our carrying capacity, which was 25,000 x. And again, you can multiply this out if you want and combine the terms. That's up to you if you want to do that. Let me just, let's say if we multiplied this in here and that out there, that would be 0.4x. And I got something like 0.00016 x squared for the equation. And so that would be our equation. So that our differential equation. Then we could solve the differential equation to find the equation of the number of fish in the pond at any time t. Let's make some other changes. So suppose people are fishing in that pond. And people catch, let's say, 100 fish per week. How would the model change? The first one, when we look at the model that we had a little bit ago, we got it to the point that it looked like this, except now they're going to be catching 100 fish per week. So now we could change this into 52 times 100 fish. So that'd be like 5,200 fish a year that they're going to catch. Or we could maybe just turn everything here into a per week rate. So first of all, we want to add this catch of fish. So let's subtract it. And this would be the same whether you do everything in terms of years or in terms of weeks. So again, this would be the amount of fish harvested. I'll just call this H. And so if we put this on a per week term, say, let's make our model where T is in weeks, then we're gonna have to change our rates. So like over here, then if we're using the same situation, then R before was on a per year basis, we're gonna have to divide that by 52. That's about 0.0077. That would be the increase of fish, the rate of increase of fish per week, change everything into weeks. And now K is going to be the same. Remember, that's just the maximum capacity. That's not going to change. So R is changing. We're already given the fish is in a per week basis. So in that case, our model becomes then we put everything into our equation. We would get for the rate 0.007 1 minus X over the carrying capacity times X minus our harvest, which is 100. And again, notice this harvest is constant, unlike we have over here. We're not multiplying this by anything because we're just saying there's going to be a fixed amount every week going to be taken out. And again, this amount of harvest, that could be dependent on other things. So you could maybe multiply this by some amount. For example, it's going to be easier to catch fish the more that they're in the pond. So this harvest, you could maybe have it in some way varying. You know, that H, that harvest rate, suppose H is based on the number of fish in the pond equal to the carrying capacity. And let's say it's otherwise proportional, say, to X somehow. Again, there are a lot of ways you could do this. And so what I did here, I said, instead of having just minus H here, we'll multiply this H by X divided by K, the carrying capacity. So what that means is there's a number of fish in there is equal to the carrying capacity. This is going to be 1, and then they'll be able to harvest whatever H is. Say in this case, it's going to be 100 fish. On the other hand, you know, if X is maybe 10,000 and the carrying capacity is 25,000, then this is going to be proportionally less times H, which again, that would make sense, is that the less fish there are in the pond, it's going to be a little bit harder to catch the fish, and this could go down proportionally. Now, there are a lot of other sophisticated ways you could put this term in, but this just kind of gives you an idea of some things that you could do with it. Then for our example, the equation would look like this. We have our rate, our carrying capacity. Then over here, we have X divided by our carrying capacity times 100. And you can multiply this out and simplify things. And again, there are many other ways of extending this equation, putting other terms in here to make it more sophisticated, more accurate. But this just gives you an idea of how to set up these kind of equations, the thought process you would go through.